Well, thanks for coming to hear about this. Let me start out by warning you and apologizing that I'm not a statistician. I am on the faculty on Princeton's interdisciplinary program, but as far as research goes, I've written maybe 1.5 papers as a statistician. The reason I'm talking to you about this is let me take the opportunity to deliver a brief version of my favorite rant about statistics, which is a reason that I think you should be interested in this topic. Is that I strongly suspect that if we somehow knew that God told us all the wrong results that have been published and why they were wrong. By far the most common reason would be misuse of statistics that form or anything else. It's absolutely rampant. If you look through any issue of the astronomical issue of nature, science, across the there's statistical errors all over the place. All the things seem to be more mistakes than getting it right. If I don't turn this on, there's going to be no sound.
Okay.
So I'm going to address just one aspect of that, for I don't want to call them lectures, but I'd rather call them workshops or seminars or something. Interactors that we use problems. And I have very little idea of exactly everyone's level of expertise and information in this subject, so I could easily be telling some of the things you already know. But I'm going to try, at least for this first lecture, and giving a kind of general context of the information. Let me say a little bit about what I won't be telling, which is solutions to some of the most common types of statistical errors we see in the literature. Let me just name 3 to give you an example we won't talk about. One is evaluating statistical significance of something observed a posteriori, meaning you look at a big data set, you notice something interesting, some correlation, some relationship between 2 things, study, maybe, in this case, some linear correlation. Typically, one then applies some test of statistical significance to the data and says, oh, this correlation only has a chance of arising randomly if these 2 variables are unrelated with 5% or less probability, 2% or 1% probability or something. Absolutely not. Completely misleading. Because you would notice the correlation before deciding what test to apply. In other words, if we took a lot of random data and you look through it for different possible correlations, different combinations of parameters, there's many possible correlations you could discover, and then pick out one. This is basically the source of numerology and conspiracy theory. You notice sometimes in that aspect of by chance, the usual sort of example is what's the chance that exactly the people that are in this room are in this room, and the people that aren't in this room who might have been aren't here, and if we evaluated that some statistic about we come to seminars and things, we find that this is an extremely improbable event, no matter who we see it. John McCall, for a while in the 1980s, kept track of results published in the astronomical literature with 95% or better significance. And then were later, and then some of them were later, a few years, either confirmed or contradicted by further data. And of those that were either confirmed or contradicted, about half of those, 95% significant, were actually correct. This is a problem in exploratory data analysis, which does not really have any clear solution. And real-life cases are often foggy because it's not just that you've compared a lot of numbers and found a correlation. You may have some idea in advance, but it may be vague about that might be correlated, it may or may not have physical sense. So there's lots of issues like that. I shouldn't go on too long on these two examples. Another very common mistake all the time is assuming errors are distributed in a normal and Gaussian way. I would say the large majority of error distribution are not normal. The Bayesian prior, but I would have myself, if you have an error distribution, not Gaussian. Things are only Gaussian if they're produced by some large number of additive independent things. So you have a central limit to them. And they go Gaussian out in the tails most slowly, often where you care the most. So you have to add together a lot of things. And it depends on how those things are distributed, how quickly they become Gaussian. So variables, if you add together numbers or things that say have a very skewed distribution or bivariate or something like that, the convergence to a Gaussian distribution is extraordinarily slow, again in the means, and evaluating significances, measurement, confidence intervals, and so on, is terribly sensitive to that presumption. Bayes does offer some ways of addressing it. And perhaps one of the more pernicious and easily forgiven mistakes is that the assumption that noise is Poisson noise. Almost all real physical systems, if you take the noise output and take a power spectrum of it, white noise, Poisson noise, independent noise, we have a flat power spectrum, space or space, and almost any real physical instrument has a ring component to the noise and intrinsic sources of noise, like if you look at noise on the surface of a star, velocity noise, like the exoplanets are interested in, the fluctuations or something real physical, generally have more power and low frequencies than independent noise. In fact, many errors are correlated. And this carries through to produce overestimates generate significant percentages. So those are just some three general ways that we get into trouble, but let's now turn our attention to Bayes' theorem and Bayesian statistics and talk a little bit about what that means about this. And again, please interrupt me if all of this is terribly familiar. So let me first invite you to think about the following situation. There's some infectious disease going on, dengue fever, let's say. It's something reasonably relevant recently. And you're a doctor, I'm your patient. You have a test for this. It's a 99% accurate test. That is to say, if I have dengue fever, with 99% of the time it will yield a positive result, and 1% of the time it will yield a false negative. And with a symmetry that most medical tests don't actually have, we'll assume that it's the other way around too. If I don't have the disease, 99% of the time it will be a negative result, and 1% of the time a false positive. Now, the question is, you've given me the test, it comes back from the lab positive. That doesn't seem like it. So what's the chance I have the disease? What's the chance that I have the disease? it's a trick question. I don't know how we should be asking you. What's your first intuitive impulse? 99%. That's what we do that all the time. By the way, the scary fact is that if you ask doctors, it's going to be 20 medical examiners, and all say that. Which is really reasonable. It's not right 99% of the time. So give it to me. It's right 99%. I've not given you enough information to know what the chance I have. It could be anything. It could be 100%, it could be 0%, it could be 50%. Those of you who have seen people are familiar with Bayesian reasoning. The reason is we don't have enough information to find it. Because you have to know what the incidence in the population of the disease is in order to make some estimate. In other words, suppose only 1% of the people have the disease. They're probably an overestimate of the actual population. That's something I'm worried about it. That means that, let's say there were 1 million people that you tested, you would get about 1% false positives. Let's say you got roughly 1 million, they all almost don't have it, so you get about 10,000 false positives. There would be about 10,000 actual cases, so 99% of those would give you a correct positive, and so of the positives, about half would have it. I see a few frowns. Does that seem clear to everyone? Suppose it was the test for smallpox. Smallpox has been eradicated. There are no cases anywhere in the world, and haven't been for decades. But if you have a smallpox test, it still has a false positive rate. Every single, and it's, even if it's a very good smallpox test, it has a tiny false positive rate. Every single positive will be a false positive, so on. So that's what Bayes' theorem is about. It lets us take into account the data. If we know what the population is, we know what the incidence of the disease in the population, you could have made a guess at the chance I had it before you did. And Bayes' theorem is to be just a mathematical way of using that prior information. Now, of course, you may be thinking correctly that, well, how do I know the incidence of the treatment of the overall population? Trying to determine, that's what we're trying to determine by doing these tests. And the answer is you don't necessarily have that. Or suppose now is well informed on medical statistics and actually knows the incidence of the population. His colleague, Naviki, hasn't done his homework and doesn't know what the incidence is. They would make different estimates of what the chance I have to disease would be, or if one of them had good or bad information. So let me come back to that a little later, but much of the problem is the reason that it's unpopular for a long time is that the choice of the prior is often arbitrary and uncertain. Various possibilities. For example, just to give an absurd case, suppose the chance I have the disease is some number between 0 and 1, of course. Well, instead of using it as a prior and the fraction of the people in the population that have it, suppose I just use, instead of all the numbers I have ever seen in my life, for any purpose or meaning, this is just a chance I have the disease, which is going to be another number out of that sample of our numbers. So why don't I just try using all the information I have about the numbers, and whatever distribution of the number seen in that interval happens to be, that could be a prior too. Or suppose I know that the overall incidence of disease in the population is 1%, but I have a reason to suspect that, let's say, more males than females have or more people in this age range, more people living in this city than that city have the disease. So there's a variety of priors to make an estimate. And the extent to which they make sense, some of them are absurd, like ridiculous, but the distribution I might want to take into account, whether patients, it's the city or in the countryside, whether they work indoors or outdoors, spread from mosquitoes, and a variety of other factors could be taken into account. So there's no, typically in a problem when you use these, you're faced with not having a single satisfying, precise answer. And you'll see as these more seminars go on, I think other examples of that, and I think give you one today. Okay, before turning to slightly more specific discussion about these, let me give you an argument why you should be Bayesian that amounts to it just being common sense. Suppose I were to tell you that I came to Tokyo 5 weeks ago on a Boeing jetliner from Newark to Narita, United Flight 79. Would you believe it? What probability would you assign to that? Not 100%, I could be lying, but if I have, if you're not aware of any reason that I would be lying, you would probably say that's likely true. Suppose I said, well, actually I came to Tokyo 5 weeks ago riding on the back of a fire-breathing dragon that flew me from Princeton to Russia, and in the middle of the night after I know probably you wouldn't assign lower probability to the airplane. But the evidence is exactly the same. Which is what I said. And that makes it silly, it is, of course. But that's all the Bayes' theorem does. In situations where you can assign numerical probabilistic values to something, it lets you automatically put that into account. So in that example, lots of people on an airplane, and you probably know dragon, and so that's the reason that we're thinking that way. It makes common sense. Now, if we actually come to a calculation, Bayes' theorem would force you to actually try to use it to say explicitly what you thought the probability of me flying on the dragon was. You might set that to 0. Perhaps, but if you're a little more open-minded and maybe you would assign it some very small number, or maybe you would say, well, the total number of people I know, how they've come back and forth, and so and so, and the chance that I would have missed it if somebody, you could try to assign some tiny little number. Maybe there's calculate some quantum fluctuation. This happened. Huge number like the people think about profit principle and so on. So again, there's this ambiguity in the prior, but the result would be about the same. So now, Bayesian statistics, the way I'm presenting it might sound like an obvious one and only simple way of doing statistics. Why would we do something else? But in fact, it has been over the history of statistics. The history since the paper here, I think it's 63, that has been quite controversial. And if we, in the middle of the 20th century, in 19th, we wanted to start a brawl among statisticians, all you had to do was, walk into a room full of statisticians and say Bayes' theorem, and then duck out the door before the punches start flying. It has been, for most of that time, considered a inferior approach to statistics to what's usually called the frequentist approach, or sometimes the classical approach to statistics. So let me just say a little bit about what the differences are. So first of all, let's just think of a simple case where we have some parameter theta we want to know, and some data x from which we want to determine it. So in classical statistics, theta is regarded as fixed. That is to say, it just has some value in nature that's determined. In Bayesian statistics, it's considered as a random variable. In other words, it's characterized by a probability distribution function. The data x are just the other way around. Despite the fact that you've already measured the data, from the classical approach, you regard the data as having been chosen from some, as a sample of some distribution function. And you consider the case where you might have repeated the experiment would have given you a different set of data. In Bayes' formulation, you regard the data having been observed as fixed. It's just whatever whatever the data you got x are, that's what they are. And so, and then you have distribution functions. And here's the most critical difference. The distribution function that concerns the only distribution function of interest in classical statistics or frequentist, this is the same as frequentist, is the probability of the data given the model. So we simply say, if theta, for some value of theta, if something is true, if the model's true, if the temperature in the room is theta, and we've made a bunch of measurements of it, randomly distributed, what's the probability that that temperature gives this result? That, in the medical example, is the probability that if I have the disease, the data will come back positive. Or if I don't have the disease, it will come back negative. Or vice versa. It's that distribution. Bayesians use that distribution too, and it's called the likelihood or the evidence. They use this distribution. Oops, I wrote that backwards. Something I will do frequently. They also have this distribution, the probability that the model is correct given the data. And that, of course, is what we really want to know. I want to know if I have the disease given the data, not, we want to know if the quasar's redshift is 7.34 given the data, not if the quasar's redshifts were 7.34, what's the chance we get the data? And they have one more, less interesting, which is the probability of getting the data. That's often hard to know, but as it turns out, isn't so important. And finally, this troublesome one, the probability before the data, independent of the data, that of the model of theta. So that's this prior. That's the probability I have the disease before we do the test. It's the probability that the temperature in the room is some value without any measurements of the temperature being made. Now, all Bayes' theorem, of course, you probably can all write it down. Just uses these distributions like this as the probability of so just the probability of the data, I mean of the model given the data, is the probability of the data given the model. So this is the likelihood. This is where the frequentists go. This is the forward calculation from a hypothesis and a model to predict the data. This is this bothersome prior. Bothersome, I say. Essential, losing. And often somewhat arbitrary. Judgment call can vary from even one person to another. Reasonable people can disagree from prior and so on. And this down here, the probability of getting the data, if you had a lot of realizations, you could think of it, is not, it sounds very hard to calculate. In many cases it is, but normally you can just regard that as a normalization parameter, and you can just calculate the top part and then require that this is normalized by whatever value is required. So that's the standard procedure there, although sometimes you can work it out, and it's sort of cute to see that it comes out okay. Now, this is a perfectly straightforward equation to use and a simple thing to do. One of the reasons there are so many errors in scientific papers, even in the most quantitative fields, is I'm afraid that the equations in statistics are often very simple. And physicists and astrophysicists and mathematicians and others who are used to dealing with equations typically have a look in a statistics textbook, or they look at the equation and they think, oh, that's easy, I can handle that. There's no need to, be very careful about it. They're easy equations. And indeed, the mistakes that you find in the literature that are due to bad statistics are not mistakes of calculation. They're not mathematical mistakes at all. They're mistakes of logic, of thinking. So, typically people are making logical fallacies or just thinking in a fairly sloppy way when they do their statistics, doing things like assuming the errors are Gaussian distributed without any good justification for doing so, or forgetting that A implies B is not B, does not B implies A, does not follow from A implies B, things that simple, the a posteriori thing. An advantage of Bayesian statistics is that it forces you to be very explicit about your priors and so on, and your thinking. To use the equation, the rigor of putting it into the equation often helps people think very carefully about exactly what they're assuming and what they're, what questions they're asking. It's not a complete cure for that, but it is useful in that way. Is everyone bored to tears at this point? There have been no questions or comments. Is it useless, useful? We're getting anywhere? Sorry. Everybody's shaky and not, but a few more nods than anything else. So, okay, let me go on.
We'll just digest.
We'll just digest. You're what?
We'll just digest.
Oh, digest. Well, my Bayesian prior on speaking to audiences in Japan is no question. Unless Masataka's here. Okay, so now, why was this controversial, and why is the very strong preponderance of thought amongst statisticians now in favor of the Bayesian approach? Well, the most obvious answer is that this doesn't really answer the question most scientists want to ask. I don't want to know the probability of getting the data in the model. I want to know the probability that the model is correct. But to a large extent, we have the use of classical statistics is based on making the either explicit or implicit assumption is equal to P of X and theta. And you can calculate that, and we just sort of go, it's probably okay. And the standard example of that is MLE, maximum likelihood estimators, are typically defined such that the estimator of some quantity that gives the maximum likelihood of the data as a function of theta. That's our usual estimator for some quantity. So if I take suppose theta is the mean central value of some Gaussian distribution of numbers, and I've measured X those, and that's my maximum likelihood estimator, in the sense that assuming theta has the mean of the values of X gives me the maximum likelihood of that, and we say, well, that's our estimate of the mean, too. That's what we think is the most likely mean. Again, that's not the case, and examples like the medical test and so on make it obvious. Mathematically, obviously, trivially, the prior is equally important. You're just multiplying two distribution functions together. It's not that the data has more weight than the prior. They're the same. And as the silly examples I've given you illustrate, the flying on dragons and so forth, the prior can completely overwhelm the data, if it has extreme value. There are nice examples of this. Do people know the taxi problem, the numbered taxi problem? Rasmussen, I think, was responsible for it. Suppose I fly to an airport in some city, some town somewhere in Japan, let's say. I go out of the airport and I get into a taxi, and I notice that the taxi is taxi number 73. On the front there it has the taxis numbered. And I know or assume that the taxis in the town are numbered 1 to n. So, there's some number of taxis there. I don't know, because I'm an absent-minded or inattentive to details astronomer. I have no idea how many taxis there are in the town, but I want to estimate the total number of taxis in the town from this one observation that I'm in taxi number 73. So what's the probability? What does this look like? P of 73, given the number of taxis, is, of course, identically 0 out to 73. And it comes up to some value that's 1 over 73. And then it goes tailing down like 1 over n. The maximum likelihood value of this is 73. So my best guess at the maximum likelihood estimator of the number of taxis, the maximum value of this quantity is 73. And what we normally do in statistics is take that as our estimate of theta. Does it seem, of the actual number of taxis? Does it seem like a good estimate to you? It's the maximum likelihood one.
Usually likely to get one. Usually likely to get one.
Well, you might think, well, maybe they only have one taxi. Well, then maybe they wouldn't number them if they only had one. But, right? Well, most people, they're different. There's no really single right answer to this, given what I've told you so far. For exactly the same reason, there's no clear answer to the probability that I have the disease from the test coming back positive. But, a different estimate you might like to use instead of MLE is you might like to say, well, I want to be above and below half the time. I want my estimate to be too high and too low with equal probability. In that case, I might want to double 73 and guess 146 or something like that. But suppose I thought that the number of taxis in towns in Japan was uniform in the log of the number, which is not so crazy actually. Then I would get a different estimate for the best estimate for the right number. Suppose I actually knew the distribution in my, I Googled it up, and here's the histogram of the number of different taxis that different towns had. Then I could plow that through Bayes' theorem and get a good estimate. Now, this both illustrates why Bayes' theorem is useful, or why it's a better approach than just classically taking the maximum likelihood estimate. Gives a slightly silly result. And you can think of examples where MLEs give nonsensical, impossible results too, if the underlying distribution is sufficiently pathological. But it also illustrates why Bayesian statistics were so unpopular for so long, because I just told you several different possible priors that you might use, and maybe the person getting in the taxi has a smartphone and Googles up the distribution, and somebody else just makes a uniform, just says, well, let's suppose the prior is just uniform in n, so there's an equal number of towns that have 1 taxi, 2 taxis, 3 taxis. Somebody else says, nah, it's going to be uniform in the log or something. All of these things are plausible priors. The reason this has been resolved largely in favor of Bayesian arguments is that to realize or maybe assert that these probabilities don't actually mean the same thing. The probability that comes out of Bayes' theorem is not something about nature. It's not something about the outside world. It's not objective. There is no probability that the number of taxis is something or another. It just is something. The town has some number of taxis, 117 or whatever. And to say that that number is probabilistic is sort of silly. Or if I flip a coin and hold it here and I say, what's the chance that the coin is when you flip Japanese coins, do you say heads and tails, or what we do in the US, or something else? Anyway, the chance that it has one side up, people will say, oh, 50%. Oh, that's silly. It has one side or the other is up. It's here under my hand. We don't know what it is. But it's not like the coin is in some quantum superposition of states that are, you know, it is something. There's no probability involved. What the probability we're describing is a description of our belief or our information about it. And looked at that way, it makes the choice of the prior, although it's arbitrary and you know, requires judgment, beliefs about things in general require that. So, you know, it's not so surprising that there's no hard single value to come up with that, you know, is the right answer. Different people will have different information. By the way, I happen to know that for American quarters, the most often flipped coin in the US, the chance of head and tails is not equal. It turns out they're not made that well. And for individual quarters can be as badly biased as 80-20. You can make money on bets and bars by spending about a day flipping quarters, and you know, find the ones that are sort of skewed off, and you test them more. You have to start with a lot of quarters, and you can find, you know, with a day's work, a quarter that's about 80-20 biased. Keep it in your left pocket. Anyway, that's so. Don't say you didn't learn anything useful.
So it could be biased either way, right? That's
yeah, it can be biased either way. But overall, quarters are slightly biased towards heads. Oh, by the way, and to do that, you actually don't want to catch them. You want to let them bounce on the floor. Otherwise, there's biases built in or from the way different people flip them and so on. So that's one reason, a sort of redefinition of what we mean by probability, that Bayesians have won out. But the more profound reason is that very nearly every classical frequentist statistic that we routinely use can be derived from Bayes' theorem and corresponds to some prior, often a fairly reasonable prior, but that you didn't know you were using. Bayes' theorem should appeal to physicists and scientists because it's sort of the F equals MA of statistics. You can actually start with Bayes' theorem and derive a large majority of, well, not all, I think now, or essentially all of the standard results of classical or frequentist statistics. And when you do the derivation, that reveals to you what the assumed prior was, and what that prior was, you then know, which you didn't necessarily know when you were just taking the average or whatever you were doing, taking the median as your estimator. There's lots of things that people do. And you can ask yourself, well, does that prior really correspond to what I believe? Okay, so we've spent quite a lot of time now talking about generalities. So will this board be visible if I use this?
So if you apply for the, could jumper code make his probability more convincing to us if he would apply Bayesian?
Fine.
If he applied Bayesian, a jumper code, if you mentioned the example jumper code, and if he would apply Bayesian statistics, could he make his argument more convincing to us?
Well, I would think so. Although, you know, instead of just writing down the predictions of papers that quoted something in 95%, he would have to put in his own prior or whatever prior he thought the authors were using. Yeah, often they're unclear. But let me now finally talk a little bit about some actual problem in astronomy and try to convince you with this one that even in the very simplest, most basic, most straightforward uses we make of statistics, we ought to be thinking about Bayes' theorem much more than we do. So, one of the most fundamental, it was supposed to be the same size, fundamental measurements we can make in astronomy is to measure the brightness of something in the sky, a star or a galaxy, in some band. So suppose I have two apertures on the sky. In the old days, these would have been holes in pieces of metal and looked at with a phototube that had a current coming out of it proportional to the light falling on it, or it could be an X-ray telescope and you can have a photon counting device. So here I have a star. Here I don't. This is just the sky. So there's some background light coming from the sky, which we take to be the same in the two apertures, plus some extra light coming from the star. We want to know how bright the star is, right? Well, let's say we count some number of photons in the sky, and here we have in the star plus in the sky. So our estimator in classical statistics is in star plus in the sky minus in sky. Oops, simple enough. We just subtract the counts here from the counts there and estimate the brightness of the star. And in this case, let's say we can do Poisson's if we want to evaluate the errors. We can do Poisson's statistic on the number of photons we've collected. That's about as simple an example as I can think of the use of statistics in observational astronomy. That's not the best estimator to use. It's a biased estimator. And is, well, to put it bluntly, wrong. Why? Anyone know? I'm half deaf. You mean the distribution of background light might be different?
Yeah.
Yes, that's certainly true. I could take into account the fact that those are, but that's even more sophisticated. Let's assume that we have a nice uniform background sky.
There's still fluctuations, right?
Hmm?
There's still fluctuations in sky. I mean, just
Yeah,
you have a background, but you measure. What you measure also has a variation.
Yeah, there's noise in this. So what I'm sort of doing here is here's counts, and here's marks or something. That's enough of it. So let's call this aperture 1, aperture 2. And so here are the counts in 1, here are the counts in 2, and I'm just subtracting them off from each other, and getting the way I'm drawing it here. And then 1 minus N2 is back here somewhere. That's my brightness of the star in this estimator. And I'm drawing it as a distribution because I'm assuming you can't. Well, let's go back to Bayes' theorem. What do we know about the brightness of the star? That's what we're interested in. That's our parameter theta. In advance, before we take the data, do we know anything?
Should be greater than 0.
Right, it's greater than 0. So that's, we know for sure that the star isn't emitting negative photons, presumably. So we actually want to chop off this distribution there. If I have low signal to noise, I will sometimes measure a negative brightness for the star. At low signal to noise, I'll just get an upward fluctuation here. This is even more true if, as you said, the sky is not constant. If we take these at different times and it's varying in time, as you often do, like when you move the fiber off the object or whatever. So we can easily put in a prior on the star, probability of n star versus n star. And let me displace 0 from the origin here, so this is 0 counts. So here the prior is just going to sit down here on the axis. No chance that it will be 0. And when I multiply that through, all it'll do, you know, if 0 was sitting here, of course, it'll just chop that off. And it will tell me that my best estimate for the brightness of the star, if I get a negative number, if I got a negative number, it would look like the best estimate right here, say, so that part would be chopped off by the product of 0 out to there. And this would look like the distribution of probabilities on the flux of the star. It'd be kissed right up against 0. Epsilon above 0 would be my best guess. But that sort of invites us to think a little more carefully. What do I actually know about the distribution of brightnesses of stars in the sky? Is all I know that they're positive, definite? What's the distribution of brightnesses of stars?
I mean, it must die down at the massive end and then has some power law distribution.
Yeah, some power law distribution. If I take you know, for instance, if I take a Euclidean space, let's just do something maximally simple, then I know that, and let's talk about flux or something, then I know that d log n star d log n, you know, let's say minus that is equal to some exponent q, say, and that's minus 1.5 for Euclidean, uniform Euclidean distribution in space, just the 3/2 power from the 1 over r squared and the volume. I could use that for my prior. I'm pointing at the wrong diagram. This for the prior. You know, I could use this power law thing that goes up here towards 0. What happens if I do that? Well, there's a little calculation you can do, which David Hogg and I actually published in 1998 or something, if you can believe that it had to wait until 1998 for anybody to do this calculation to get the sense of. By the way, we're talking here as sort of maybe first-year statistics graduate student level sophistication. This is not fancy stuff, not even close to fancy stuff. Let me just look it up. So you can make, I could put this on the screen, but I don't think it's actually, you can, it's Hogg and Turner. 1998, and it's in publication of the Astronomical Society of the Pacific. An obscure publication. The app didn't think this was interesting enough for, or important enough for their journal. It's too trivial. Nevertheless, how many of you, despite the fact that this has been known for 17 years, how many of you make this correction when you measure the flux of something? What? Anyone else? Or you just subtract the background? Anyway, as I should have already said, this term as probably most of you already know, this term, as I've said, is the likelihood or the evidence. That's the prior we talked about. This is the posterior. So that's the probability distribution from the model. having the value of the brightness of the star in the case which we're looking at. So let's take an example of Q equals 1.5, Euclidean slope, and draw the probability of S over S observed. Observed is just the observed number of counts. This is the true number versus S over S observed. And if this is a function of the signal to noise, and if you make a signal to noise of about 10, it looks pretty nice and Gaussian, and you didn't go very far wrong just using the standard thing. If you go down to a signal to noise of, and this is centered close to 1, if you go down to a signal to noise of about 5, this is displaced in this way a good bit. Go down to a signal noise of 3, it looks like this. The probability that there's no maximum, it runs away, the posterior runs away towards infinity as you go down to zero slope due to the infinite number of very faint sources that power law implies. Now, of course, in the real universe, there's not an infinite number of faint sources that for one thing, gives you divergent sky brightness, Olber's paradox, and all of that. So at some point, this power law turns over. The actual power law distribution of S times S. The power law looks like this, and somewhere up here it turns over. And you can turn it back down depending on what's going on. And the maximum would sit there somewhere if you did that. So your best estimate is nowhere near that signal to noise is less than 0. I mean less than 3, or somewhere between 5 and 3 it blows up. It turns out this is all done analytically in the paper.
Sorry, so don't you also have to consider the case that maybe there's no object there?
Well, yes, I suppose you could consider that there's no object at all there. The example we're imagining here is that you essentially are not allowing for that, but in a sense that's all. If you don't have any data other than the same measurement that you measured the flux with, then right. I can imagine situations. This comes up in the Hubble deep field where you can stack the images and detect objects at high probability, but then you want to measure their colors. Mm-hmm. And maybe in the individual bands you don't have such good signal to noise, so you need to make these sorts of corrections. Or should I put in the prior for the distribution of colors and not just the prior for the distribution of fluxes in each case? But here's a couple of handy little. So the maximum likelihood S over S observed is equal to a half plus a half times root 1 minus 4Q plus 4 over R squared, where R squared is the signal to noise. I'll use S and N for everything, so R squared minus signal to noise. And if R is fairly large, it's approximately equal to 1 minus Q plus 1 over R squared. And that's for R squared much greater than 4 plus 4. Okay, so the obvious expansion there. That's a small number. So this is something you should be sticking into all of your photometry codes all the time. It's a handy little simple formula to use. But anyway, I don't want to make too much of a thing out of this. It does lead to systematic errors in photometry of faint objects that are rife in the literature and could easily be fixed. With the ambiguity, one reason people don't like to, again, just coming back, don't like to do this is, well, maybe, since you're measuring faint sources, maybe you don't quite know what this distribution is. It's not necessarily 2 equals 1.5. In fact, it probably isn't. And for faint galaxies, it's much shallower than that. And you care about what it is below the limit that you're observing for a typical object. So if I'm talking about some really deep survey, Hubble deep field or something, then it's model dependent and so on. And so observers don't like to publish measurements which depend on models or assumptions or theories about what the faint counts are, extrapolations and so on. That makes you feel a little queasy. That comes back to why Bayesian statistics are not so popular. But it doesn't seem like our measurement of the brightness of the star should depend on a model of what K correction, or let's say of a faint galaxy, a model of what K corrections are in faint levels, which affect the counts. But nevertheless, it's a better estimate. It will be right more often than just subtracting the two, which gives you a biased estimate. And I think I'm up to the end of my time and slightly more, so I'll stop there and we'll continue, I think, next Tuesday. And but I'm happy to answer questions now or talk to people. Next week and so on. So happy to chat about these things. But I hope this really simple example convinces you that you don't just have to worry about Bayesian statistics when you're fitting 11 parameter cosmology models to measure microwave background measurements and deriving some multi-dimensional thing within CMC and all of that. It runs through simplest uses of statistics. Thank you.
In case the quick questions, maybe a couple. If not, let's postpone.
Have you already excluded the value of the negative S?
Yes, because this.
Maximum likelihood
Yes, we have taken out.
You have already put the plus minus to estimate.
But this has no probability of having 0 form. Simply because we assume that it's chosen from this distribution that has an indefinite power. Somewhat alarmingly, you get a different answer if you do this in magnitudes and not fluxes. But maybe we'll talk about that again later. MLEs are affected by the metric of the space.
Okay. Let's continue either in tea time and so on, and the lectures will continue next week. Right? Okay.